Yeah, I think everything is fine. Am I audible or not? Yeah, voice is clear now. So, today my aim is to discuss some topic related which title I am posted on YouTube. That is neighborhood, open set and closed set and anything. So basically today topic is just nothing but hold on few second I'm start this. Yeah, all thing is completed. Yeah, here is the topic that is transfinite number. So basically, what is transfinite number and how the implementation on real analysis? Let's check it. Okay. So here you say that for any infinite set, you know the infinite set very well. For the infinite set, we adopt a symbol to denote the cardinality of that set. It is nothing but it is only a symbol that adopted by various mathematicians for representation of cardinality of that set. Okay, these symbols are called transfinite number or cardinal number. Here is the basically some note about transfinite number. The transfinite number is nothing but the note says that here is the set of natural number that is infinite set. So we adopt a cardinal number like this, that is psi alpha alif naught, where alif has the cardinality of that set. Okay. Next, here is one more note. Alif naught is the smallest transfinite number, as one is the smallest counting number. Okay, because very important in natural number series, the one is very least number, and second is the second number is I think the only counting number it is only. So similarly, Elif naught is the smallest transfinite number and second transfinite number is continuum hypothesis. So first one is our transfinite number says that we denote here the Alif naught. Alif naught is nothing but the smallest transfinite number Alif naught. That is, if 1 is the smallest counting number and 2 is the second number, then alif naught is the smallest transfinite number and second transfinite number, that is C. That is, we say that here the continuum hypothesis. That is, if a cardinality of a natural number that is equal to alif naught, and here is the set of real number that is also a continuum hypothesis. So one thing is that the number here, natural number, cardinality of natural number which is less or equal to less than cardinality of real number. So alif less than continuum hypothesis. Next note says that two infinite set are similar. Okay, why? Because if they are the sum transfinite number, then we say that the two infinite set are similar. That is, n is this not similar to r because alif naught which is not equal to c. One more not related to the alif naught and continuum hypothesis are two transfinite number, means infinite set are of two types. First one is countable set and second is our uncountable set. So these are two basically based on the two transfinite number, that is alif naught and continuum hypothesis. Now move on the next point, that is our countable. So what is countable set? Any set A is said to be countable if it is infinite or countably infinite. It means if any set, let's take one example here. I think I am put here example. Yeah, here the countable set of across n. So now take here the element like take here 1 comma 1 1 comma 2 1 comma 3 as it is. These are the numbers. And second block, that is 2 1 this type also the number. These are not the n cross n representation of taking here the natural number one block and second block is also a natural number. So when we multiply both together, then we get a countable number. And here the representation of arrows is that there is the only two number, which is basically n cross n represent as the countable number. Here is the only two, three number because here the when we take there are two set here, and now the as it is here the four and here the five and so on. Okay. So basically, some countably infinite. What is there? The two. What do we say that? Here, the first one is a finite, or second one is countably infinite. First, I am check on YouTube. Then I am proceed this. So okay. So basically, some okay. Now, what means by countably infinite? Countably infinite is nothing but it is the set A. Here, take any set A is said to be countably infinite if it is similar to what means take here the only set A, okay, and set to be countably infinite if it is similar to set of natural number. It means it is similar to set of natural number. Okay, so they can be written as the this type of format. Here the set elements are like this: A1, A2, A3, so on, AR and AR plus 1. These are the written as the formats its element. Okay, so we can label it as A1, A2, A3, AR and AR plus 1. And it which is not countable because yes, the only element here when we put here the A R, that is the number. When we take here the one A1, A2, A3, these are the called the not countable. So we can say that it is a uncountable. Okay. So one note says that term countable means count the element first. Okay. Rather when we write like this, the countable means what? Countable means what? Count and change the color of pen. Right. First one is what? Count the element. Count the element, that is if we label element of the set, so it should be treated as like this. Okay, that is our countably infinite. Next one here the n cross n of is countable. Now here the summation was what is n cross n gives us. So here we can label the element of n cross n by playing the element as first put those elements whose component sum is 2. What it means? First put in first put as element which have whose component sum is 2. After put those elements whose component sum is 3. Okay. So that is here the number written as 2113. Then put for sum 4. Okay. Now that is 312213. That is the when we put here the number component as it is. I think those element their component is 3. Then we like this the number comes. Okay. When we put the sum 4 here we write here. When the number is sum is 3, okay, that is 2 comma 1 and 1 comma 3, like this number comes. And when sum is 4, then put here 3 comma 1 comma 2 comma 2 comma 1 comma 3. That is similar to the label of element, that is n cross n. So hence n cross n is our countable. Either one note is either by defining the bijective between A and N, or by labeling, we can show that A is countably infinite. So that's assumption which is very helpful for finding the countable number as well as the uncountable number. Okay. Now take one example here. An example says that take a set of natural numbers similar to set of integer. Okay. So here fn is what the number we take from natural number, and for even input we take here n by minus n by 2 type of element put here, and when we take a odd n minus 1 by 2 input here. So f is 1 1 and on to his n is similar than z. Okay. So that is the n is similar to set of integer. Now one more example say about the rational number. So app mapping q plus, that is the countable number there are the representation for the n cross and take here the element, and such that here the when you put a rational number then p by q the format are come. So f is 1 1 1 2 1, then q plus is a similar to n cross n type element. But it means what? It means take here the number that is from n cross n type. So where we put here the p by q type of element. The p by q type of element comes in our rational number. So here the which is equal to the p comma q type of set has come like this. When we put the n is equal to p, and second one is q. So it's also the similar set and similar here we find like this. So n cross n is countable. So q plus is our countable. Now move on next slide. A set of even integer. So then set of integer, it means the number multiple with two that's number are comes like the even integer type. So take here this as that fn is equal to 2n and f is 1 1 and on to go. So here this also the natural number which is similar to even set of even integers. So one note more said that here the whole cardinality of two similar sets are always equal. So how can you say that the cardinality of two similar sets are always equal? So if the representation of many, like first one is a natural number, rational number, integer, n cross n transfinite, or n cross n representation of natural number, q minus q plus n whole integer like this. So the one thing is that the cardinality of two similar sets are always equal. So says that like this. Okay, these are the also comes which is equal to the whole number which is equal to the alif node, then we say that it is the countable part. Okay, now move on next slide. Next slide says that every infinite set has countably infinite subset. Okay, everything is fine or not? First time check on YouTube, then I proceed my lecture. Happy Holi to all of you in advance. Every infinite set has countably infinite subset. Okay. Yeah, I hope everything is fine. Yes. So every infinite set has countably infinite set. Now let's check this proof. First one, take here the let x. X is what our infinite set. Okay. Let a belongs to a x. Name it as a1 and construct a1 which is equal to a1. Now choose x belongs to x minus a1. Name it as a2. First one is here x is in let x is infinite set. Then it belongs to x, called it at a1. Okay, and construct a1 which is the singleton set of a1. Now second case is take here the x belongs to x minus a1, name it at a2, and construct like this at its a1 union a2 in singleton set. Now so on, we can construct for a n minus a n which is equal to n minus 1 union a n. So here first thing says that for any n belongs to a natural number x minus a1 which is not equal to 5. So hence T which is belongs to x minus an. So an plus 1 which is basically which is equal to what? An union an plus 1 like this number. So every infinite set has countably infinite subset. Now move on next part. Now take union of for all ai's. Okay, so take here the A which is equal to union of I belongs to natural number, and AI which is equal to A1, A2, A3 like this element we put here. So we say that it is the countable. Means every infinite set has countably infinite subset. Are you understand this? And keep in your mind. First thing is that in this proof, first things what to do. Well, let's take X is infinite set. Now here right I'm based on flowchart. If the student is from CS background, we understand already the flowchart. What it flowchart? It means a step by step instruction for any algorithm. Take X. X is our infinite set. Okay. Then pick one element A belongs to X and construct T dash A1 which is equal to singleton of A1. Okay. Now choose one more, that is X belongs to X minus A1. Name it as A2 and construct it in the form of A2 which is equal to what? A1 union A2 like this element. And when you proceed on for the an basically what? An which is equal to an minus 1 union an like this term marker. So so on for any n belongs to natural number x minus a1 which is not equal to 5. So hence we can say that t belongs to x minus an. So lastly an plus 1 which is equal to an union an plus 1. And now move on next slide. The next part we says that for ai's type of term are when we put here the input like this ai's type of event then whole union, then it is, we can say that it is a countable part. So hence every infinite set is countably infinite subset. Now here the one more note. One more note says that if mapping from A tends to B is 1 1, then they are the cardinality of A which is less or equal to cardinality of B. Then there exists X belongs to B such that we can say that A is similar set of X. Okay, I think I hope you understand these terms. Now next notice is that if mapping from F mapping A tends to B is onto here the regarding about one case in every regard say about onto case. So in onto case take here the portion which is cardinality of A which is greater or equal to cardinality of B, then there exists Y which contain A such that P is similar set of Y. Okay. Now move on next part, that is one result related to this. Every infinite set is similar to at least one of its proper subset. So how can you elaborate this? So now move on this part. Every infinite set is similar to at least one of its proper subset. So that is X is an infinite set. Take here one X is infinite set, then there exists y contain x, and such that we can see that y is a similar of x. Now one more, that is if x is infinite and e is in a finite set. Here say about infinite set and here say about the finite subset of x. Then we say that x is similar of x minus a. The whole course based on the CSIR-NET based exam. Okay. Also, this concept used in IIT JAM exam and many other like this TIFR. So, all concepts are used in many exams, but questions labels are different only. Concepts are unique for all. And some changing about when we combine a real analysis with complex question asked about the in NBHM type problem. So in next part, here we say that I am asking about the result and teach about the result here. So that is x is in for infinite set. Now take like this here, when x is infinite set. Okay, then there exist, hold on, I am right here e, then there exist y contain x, and so that we say that here y is similar a set of x like this. And next one is things if x is infinite and ab x is infinite, okay, and ab finite subset, then both combine together for x, then we say that x is similar of x minus a type element of constant. So that is when you take a closed interval of 0 comma 1 which is similar than 0 comma 1 open interval, and here the x is a member of finite infinite set, here the closed set are come, and a is a singleton of a 0 comma 1 set like this, and a minus x is equal to 0 comma 1. Hence you can say that if the similar whole, then we say that it is a countable like type of element account. Next result says that every subset of countable set is what? Countable. Very famous and most important result which is asked in exam, CSIR-NET type of exam. One more result related here, Cartesian product of two countable set is countable. Okay. So already you've seen in a transfinite number when I discuss about countable infinite and countable set, and we see that the mapping like this. So these are the countable set. Next one is countable union of countable set is countable. Now move on next part, that is one proof based on the countable. So here the countable union of countable set is countable. How it is? So take here the set AI which elements put like this for AR1. Okay, I is nothing but the implementation of 1 to 3 number used in here. Use here. Each AI is countable. Then element of countable union. Okay. So element of countable union of set AIs can be listed as A11, A12, A21, A13, A22 like element put here. So I plus j which is equal to k, and k the element are like this 2, 3, 4 element when you put here the element, because when you add I and j then which is get you get k. So that is for this type of sets representation like this for union countable union of countable set is countable. So it is also a countable. So hence we say that countable union of countable set is countable. Now move on next part, that is one more based on uncountable. Okay. So here the late AIs are set with at least two elements. Hold on. Here are two sets with at least two elements, then infinite Cartesian product is uncountable. First one thing is that all result all not must be remembered and keep in your mind for the any competitive exam, because the all questions are basically based on result, note and sub concepts regarding. So that is xi denote 2 points sets here for all I, that is product of, and say that infinite Cartesian product of is also countable. Now one more result, us say that following statement are equivalent if S is countable set. Second thing is there is surjection. Surjection means onto, and onto which belongs first number and some countable set. Okay. Third, the direction of S into M. So are also result part here is the algebraic number, because number basically in two parts. First one is transfinite number and second is algebraic number. Finite number we discuss about there are two types, countable set and uncountable set. Here the portion of algebraic number, but the expression like this to under root 2 is a number as written like this. When you have some number like this, real and some coefficient are come, then you say that a real number is set to algebraic over rational number if it can be root of polynomial equation with rational coefficient. Okay, so one note related to this, any number of that form like this under root of p by q is algebraic format and are all algebraic number. The set of algebraic number is countable. Okay, this note is very important because here they say about the algebraic number is countable. Now move on one more important theorem basically based on the basic exams like your B.Sc, M.Sc. These questions are uh, always asked in your uh, DD exam or any university's type of exam. So the theorem says that the unit interval 0, close interval 0, 1 is not countable. So here is some proof regarding this. Proof say that these number take as a countably infinite. If number is countably infinite, then also say that it is uncountable like this number comes here. So take number because in mathematics first you take a contradictory, then you prove that it is a true for countable or not countable. So the clear statement say about the not countable, then we find for uncountable, and for uncountable take care the countably infinite. Then element of 0, 1 can be represented by labeling like this. So here the x and n belongs to natural number. Let the labeling like this belongs to 0, 1 and each xi can be expanded in the form of an infinite decimal. So we have for x1 element belonging like this x1 0 dot a11 a12 a13 a14 like this number are comes. For x2 like this number are comes and up to xn these are the so on the number are comes. Here each aij belongs to like this number 0 1 2 3 4 5 and these number are comes like this. Okay. Now move on next part. Now consider B with decimal representation. Now here the decimal representation for B, that is B1 is any integer of the form 1 to 8 such that Bi not equal to A11, for B2 such that B2 which is not equal to A22, and so on the number comes for like B and for the okay. So here clearly say that B belongs to 0, 1 and B which is not belongs to Xn. So for any n belongs to a natural number, so decimal representation of B is different from the decimal representation of Xn as Bn which is not equal to An. Hence sometimes is wrong, so our assumption is wrong. So we say that it is a number here. The unit interval is not countable and say that it is a uncountable. So first thing is that in this theorem, say that the theorem say that the unit number 0 close interval 0, 1 is not countable. So here hence we prove here the number is uncountable. Now move on next part, one more result related to this. Result says that if AI is an uncountable set, it means non-enumerable, then union of AIs and AI are uncountable. Now move on next part, here is the one more question related to this. So that every non-empty interval is uncountable. So how can you prove this? Okay. So first thing is that now I'm going to explain this in my way. Then I'm teach you the other part. Okay. Wait for some minute. Now come to the solution part. Here, uh, 0 comma 1 is uncountable already proof in before. First thing is that, hold on, part is missing here. Actually, I have many questions related to this. Hold on. So that every non-empty interval, is uncountable. So first thing is that here you need to prove that first thing is f. Okay, f is well defined. How it is possible? Well defined, it means because in this question, so that every non-empty interval is uncountable. Okay, so first thing is that 0 comma 1 is uncountable already, you know by theorem. Okay, so consider here the one map mapping from 0 comma 1 to a comma b. Okay, and one more algebra fx, which is basically plus b minus a. Okay, so thing is that ab is here needs to erase. Now here you need to check f is well defined. Okay, and second thing is f is 1. Okay, and third thing need to check f is 1. So now my question is how you find this. Okay, well defined, it means what? It means put here f0, which is equal to a plus b minus a dot 0. Then you get f0 like this type of number or comes f0, which is basically equal to a. Okay, and then you put here 1, then number is comes like this, a plus b minus a, which is 1, then basically which is equal to what? It is equal to a plus b minus a, then cut like this, and number. And the second thing, f is 1 1. So it means what? It means it is 1 1 1 1. Then in case of 1 1 f1 fx1, which is equal to fx2 type of element comes, then put here the a plus b minus a, and terms like this, which is equal to a plus b minus, which is equal to x1. Then we say that it is also a one type of number comes, and last you need to check for onto. So as for onto, f is already proof here the one type number are comes, and f is our continuous, then f is said that it is a onto also. Hence f is well defined, one onto, so these are similar. So first thing is that when you check when you check every non-empty interval is uncountable. So non-empty interval is uncountable. So first thing is that you may be defined f. Okay. Second thing is that go for one, and second thing is lastly go for onto. And when you check this code, then you say that the given interval is uncountable. So one note related to this: if a comma b is uncountable, so its superset R is also uncountable. Now move on next part. Then one more before discuss the behavior of A and B. How can you discuss this behavior? Okay, so take one more slide. This slide I am 58. Yeah. Yes. The question say that discuss the behavior of A and B. If so, how can you discuss the behavior of A and B regarding this countable or uncountable? So first thing is that uh, take here the A part. Now here the A part. If F mapping A turns to B, okay, is onto and P is countable. When you take mapping from A tends to B is onto and A is countable, then you say that answer like this: F is onto, okay. Therefore imply if F is onto, then cardinality of A which is greater or equal to cardinality of B, eh? Okay. And if these are possible only when cardinality of V which is equal to if not, okay. So or say that it is finite, that is B is countable or finite. Okay. So next part for B, take another mapping A tends to B and say that it is onto and B is uncountable. So how can you elaborate this? If F is onto, then cardinality of A which is basically greater or equal to cardinality of B, okay, and B is uncountable. Uncountable. So A must be uncountable. Okay. So these are two assumptions. Now next one we move for C. On C part, take one more mapping from A tends to B. Okay, is 1 and A is countable. Then what? Then you maybe say that B cardinality of B, which is less or equal to cardinality of A, therefore imply B can be countable or uncountable. Okay. Now move on next part, that is our E portion. Take one more map from A tends to B, and it is 1 and B is countable. If B is countable, therefore imply cardinality of B, which is greater or equal to cardinality of A, therefore imply A can be finite or countable. Okay. Next assumption, one more assumption related to this. If mapping A tends to B, inside that it is 1 okay, and A is uncountable. Then it means what? Take here the cardinality of A, which is less equal to cardinality of A. Here A is uncountable. Uncountable. So larger will also uncountable. Here B must be uncountable. Okay. So these are the basic assumption which is basically used in the transfinite number and their type of countable and uncountable. When you take here the number like this, discussion of behavior of A and B if countable, uncountable. Okay. So move on to the next part. Which slide I am? 58. Now next part is arithmetic of transfinite number. An extension of continuum hypothesis. How continuum hypothesis behave when you elaborate for second type, then you say that the number is continuum hypothesis. So extension of continuum hypothesis. So what is extension? Extension, it means you can elaborate this with a number adding for leaf node, cardinality, power, or anything. So here there is no transfinite number between a leaf node and 2 to the power a leaf node. Here a leaf node, which is basically equal to cardinality of the natural number, and say that the cardinality number it is also denoted as card of natural number, and 2 to the power alif naught, which is equal to cardinality and card of Pn. There is no cardinal number between lambda and 2 to the power lambda. Lambda is our transfinite number. 2 to the power lambda is cardinality of our set of that set. whose cardinality is lambda. Okay. So these are the extension of one. It means what? It means first thing is that how can you needs to check like this. Here, arithmetic of transfinite number. And first thing is extension of continuum hypothesis. In this extension of continuum hypothesis, you may be there is no transfinite number between what? Between aleph naught and 2 to the power aleph naught. Okay. So here aleph naught basically which is equal to cardinality of n, which is equal to represent at cardinality of n like this. Okay, only representation. And 2 to the power aleph naught which is equal to c and which is equal to card of p. Okay. So there is no cardinal number between. So what? Second thing is that I am say that there is no cardinal number. No cardinal number between lambda and 2 to the power lambda. Okay, where lambda is your transfinite number and 2 to the power lambda is cardinality of power set. Cardinality of power set of that set whose cardinality is lambda. Okay. So basic assumption about arithmetic transfinite number, that is it is only extension of continuum hypothesis. Okay. Now move on my slide. Slide number is I think 60. Now move on next part. Here the some assumption based on it. If cardinality which is equal to lambda, here the cardinality A which is equal to lambda and cardinality which is equal to mu, then their assumption are comes like this. And maybe if you needs to write this, then take a screenshot and write in your copy. So first thing is that if cardinality of a cross p which is equal to multiplication of these two things union mu and lambda is greater than mu, then says that these are similar set for A if these are the condition holds, and for B parts these are condition for C and D like this. Okay. The whole thing says that for about an extension of continuum hypothesis. And lastly, the cancellation law does not exist. How? Because when you take here the 2 to the power aleph naught and multiply with 2 to the power aleph naught, then power multiply if cancellation law valid, then 2 to the power aleph naught and which is not which is equal to aleph naught, which is not possible. So says that which is not equal to, well, if not, then say that the cancellation law does not exist. And fourth part, exponent rule it value. Okay. Now move on next slide. Here is some examples of countable and uncountable set. So first thing is that here the countable and uncountable set their example based on like this. So set of all polynomial up to degree n with rational coefficients. It means you here take like this the number basically based on the set of polynomial which up to degree n, and second thing is that rational number, rational coefficient, and rational coefficients are only the coefficient like this a0, a1, a2, an. These are the coefficient, these are representation of polynomial where A0, A1, An belongs to Q1, Q like this and n times. By choosing one such tuple, we can construct as polynomial. So we take all tuples and cardinality all such tuple will be equal to cardinality n times. Okay. These are the basic representation of some example of countable and non-countable set. Okay. Now next thing is that hence the cardinality are S, and we know that Cartesian product are finitely of countable set. Again a countable set hence says that S is countable. Okay. So actually I need to explain in another way. Okay. Now I'm going to write again it. Now move on next slide. That is our here, what I'm trying to say you, the some example basically based on countable or uncountable set. Example of countable and uncountable set. Okay. So in first example, take one set of all polynomials up to degree n with rational coefficients. Okay. And in second example, better to be take another slide and needs to escape for explanation. And here the second example, set of all unit circle, set of all unit circle in the complex plane, with center as rational coordinate. Okay. There are various examples basically based on countable and uncountable. Now needs to explain first thing is set of all polynomial up to degree with rational coefficient. So in this example, first thing is that set for polynomial up to degree n. So take S and polynomial number like this now px which is equal to set for a0 plus a1x plus a2x square goes up to an x power 1 and ai belongs to q. Okay, and as you know, a0, a1, a2 up to an belongs to q, q cross q up to n times. Okay, so here you say it means you choose any such tuple such can we can construct our polynomial. So if we take all tuples and the cardinality of all such tuple will be equal to cardinality. Okay. So lastly, you can say that the the cardinality of S, which is equal to cardinality of Q cross up to cross Q. And as you know that as you know Cartesian product finitely okay of countable set is again a countable set. Hence say that S is countable. Now move on next part, which is set of all unit circle in complex plane with center as rational coordinates. So how can you prove this? So first thing is that take a set S which is basically equal to the set of unit circle in a complex place. You know the in complex plane the coordinate used like this a x minus a chi square plus y minus b chi square which is equal to 1. It means a square plus b square which is equal to one type of unit. For unit circle you these are the standard part you take here the unit circle for. Now x is equal to what? X minus a chi square plus y minus b square which is equal to 1. Okay, and here the a comma b belongs to q. Okay, means you can say that cardinality of S equal to Q cross Q, which is therefore implied S is countable. Okay, now there are many examples basically based on countable and uncountable. Move on now, move on that slide. Here, slide number I think 64. Yeah, here the set of all unit circle in complex plane with center as rational coordinates. Okay, so S is our countable. Now next example say that set of all circle with rational radii. If uh, radii rational radii and rational coordinates, then say that it is also countable. And for 4 point, set of all interval with rational ends points is also countable, and fifth point set of isolated point is countable, and 6 point derived set is uncountable, set is uncountable. Okay, so here the derived of countable may be anything. It means q prime which is equal to r and n prime which is equal to q. And here the set for when you put here the set for these are various important part which is connected with point continuous function. Okay, and every time asking CSIR-NET exam or other competitive exam. Okay, so one more note. If set has finite number of limit points, then set is countable, and seven-part set of transcendental number is over Q is uncountable, and eight-part, here the one more example basically based on if set of f mapping from natural number to integer set of all function from n to z to the total number of function from a to b, that is cardinality of e to the power cardinality of a, and maybe so write like this to the power leaf node which is equal to c, and s is uncountable. And for 9 part, s is equal to f mapping z2 tends to n, and cardinality of s is equal to a leaf node at square which is equal to a leaf node, and s is countable. Now one more example here, we can say that if this possible then say that s is countable. And for 10 points, say that S is equal to F mapping from F mapping Z tends to Z. Then you may be put like this now. Cardinality of S, a leaf node to the power a leaf node which is equal to continuum, and continuum basically based on uncountably infinite. Then you say that S is uncountable. Here is also uncountable because the leaf node to the power continuum hypothesis. Okay. And in 11 you say that is also uncountable, and 13 is also uncountable type of these are the basically example based on countable and uncountable only. And 14, set of all sequence with entry 0 or 1 is also uncountable. Now next part, set of all this one interval is countable, and 16 set of all finite subset of n is countable, and 17 A is uncountable and B is countable, then say that A minus B is uncountable. So here the today lecture I'm going to finish. Next lecture maybe entire set, and where is neighborhood? I think basically here is neighborhood, that is part of points of topology, and maybe I am teaching you next class. Okay, so thanks for watching these videos. Needs to change the title of this video. Okay, thanks for watching this video.